Here we go.
Mm-hmm. You got Richard Grace. Book Davies are on.
Hey, fellas, welcome.
Yeah. I don't know if you guys saw it. It was on Facebook today. Tom from Facebook Astronomy Club submitted a shot in the Andromeda Galaxy. It's almost 100 hours long.
Holy cow.
Incredible. Yeah, it's incredible. It was just shy, like 4 minutes shy or something like that of being 100 hours. I would have just shot a few more minutes so I could call it 100 hours.
I think so.
Right?
Right. 100-hour shot. Now, was he taking short shots and stacking?
Oh, yeah. Yeah, sure.
Okay.
But there's like at this one side of it is like this pink, looks like a pink nebula is in it. You know, not like where you see like knots of hydrogen alpha, but like a high, like a H alpha
Right.
cloud, Pretty cool.
That's amazing.
Yeah. Something you need.
Getting one other prop for today.
Who do we got here? We got Richard Grace, Book Davies, Senthil Kumar Nagapan,
Wow.
Amanda Z. I'm not sure who Amanda Z is, but welcome. And Martin Eastburn. And who else do we have? Harold Locke. Saw Harold's astrophotograph today. It was very nice of the moon. Billy Beckett is on. And Billy's Astro. We got the Billies here today. And yeah. So.
Awesome.
Dr. Barth is going to make you work your mind today.
Yes, indeed.
On October 16, 2017, the Lunar Reconnaissance Orbiter mission celebrates 100 lunar days of being at the moon. It's a big accomplishment. Now, you may be wondering, if the spacecraft launched way back in 2009, how are we only at 100 days? What is a lunar day, and how does it differ from a day on Earth? On Earth, a day is about the time it takes for the Earth to turn once on its axis with respect to the Sun. A lunar day is about the time it takes the Moon to turn once on its axis with respect to the Sun. And that's about 29.5 Earth days, so it's about a month. Now, you may be confused about how the Moon rotates if we always see the same face from Earth. The answer lies in a process called synchronous rotation, which is caused by tidal forces between the Earth and the Moon. We always see the near side of the Moon because as the Moon orbits around the Earth, it is also continuously turning. In fact, it rotates at the same rate it orbits the Earth, on average. So, a lunar day takes about the same amount of time as one complete lunar orbit. 100 lunar days means 100 chances to observe a complete day-night cycle on the Moon, photographing the surface with different sun angles, measuring the rising and falling temperatures, and studying the way certain chemicals react to those daily changes. If we want a better idea about long-term trends and processes on the Moon, being able to study it for 100 days and counting is a good place to start. And thanks to all the data gathered from LRO during this time, our understanding of the Moon has increased exponentially. Stay tuned for our next video that explores the significance of being at the Moon for 100 days and what we've been able to accomplish in that time.
So, Dr. Barth, was that an appropriate video or not?
Amazing.
Amazing.
Setup. we don't talk about this, guys. I give Scott a topic, and this week there's not even a download. He just has a title, and he just pulls stuff up. It's always right on point. It's wonderful.
I try with the help of NASA and the European Space Agency. Yeah, they help a lot. So. Anyways, we have we're running up against the autumnal equinox, which is going to happen in 2 days. Is that right? Is that Wednesday?
I think so. I think it falls on the 22nd this year.
22nd. So so this is it's the time where we might feel a little bit of a chill, and I don't know if you know this yet. Maybe you do. Daniel, but the weather, the temperature is going to drop, I think, starting tomorrow. Now it's almost 90 degrees outside right now.
Yeah.
And tomorrow morning, this is Arkansas for you. Tomorrow morning, it's supposed to be 45 degrees. Okay. Awesome. So that's a huge drop.
It is.
and then it's going to drop a little bit more the next day. And then it's going to climb back up to about 75 and then like to 80 something, and then back up to almost 90 over the weekend. So,
yeah, Scott, I drive a Roadster, right? No doors, no roof, no
That's
windows.
Right. Oh yeah, you got that really cool trike.
I have a really cool car, so I drive the Roadster. Yeah. So this morning I'm riding to work. It's about 62. I'm coming home. It's 94, according to the thermometer in the car. And so,
never a dull moment here in Arkansas.
Never a dull moment. That's right.
That's right.
Well, we're going to have a fun day today, and this actually comes right out of a lecture that I do for my students, and they always really enjoy it. It's kind of like bang, mind blown sort of a thing, and so I thought I would take you guys through it. They sometimes get a little bugged with me because I get the come on, just tell us the answer. No, I'm not going to.
Right.
When it comes to teaching styles, I'm a strict constructivist, which means I give an inquiry style type class where you get to discover and think and learn. I'm here as a coach and a guide. And if you're going down the wrong direction, I'm here to keep you from banging your head against the wrong door too many times. But what I'd like for everybody is to have some paper and something to draw with. And we're going to take you through something, as I promised last week. I'm not going to teach you a single thing you don't know. And I have this discussion with my young teachers all the time. They come to my class to learn to teach astronomy. Virtually none of them have any formal training in astronomy. How many people have ever had an astronomy class? About 1 or 2 out of every 50. So it's single-digit percentages. The rest of them know they've never had any. Much the same when I talk to teachers around the world. I'm teaching astronomy now. Good. How many astronomy classes have you had? Well, none. Like, how did you get the assignment? I had one more science class on my CV than anyone else. So the headmaster said, you're the person, you're the one. You're teaching astronomy next year. Oh boy. So we're going to go through this today, and it's going to be interesting. And I always start my classes out and I tell my students, you know all the astronomy you need to know. You know all the astronomy you need to know to teach this subject. You just don't know how these things fit together. You have no overall context for all the things you know. And all too often, we teach individual isolated facts. We do it because they're easy to test, right? How far away is the moon? 385,000 kilometers. Did you check the right box? You either did or you didn't. It's very easy to test this and to assess your knowledge, but we rarely ask students to apply their knowledge, to use it to figure something out or to follow a line of argument. And so that's what we're going to do today. And I'm hoping it's going to be fun. It's going to be interesting. So I'm going to, I hope the audience will forgive me. I'm going to switch my camera around. So it's going to look like a giant California earthquake for a moment. And I'm going to swing around, and I'm hoping that this will fit.
So there was a question. There was a question about why there wasn't a download today.
The answer is because we're all going to learn together. And as we learn together, then there will be a download afterwards. Scott, nature always teaches the lesson first, gives the test first and teaches the lesson afterwards. Is it okay to step on a bee on a flower with your bare feet the way you would do an ant on the sidewalk? The answer is no. And nature gives the test first. You're going to do this? Yes. Ow. There's the lesson afterwards.
Right.
Should I juggle snakes? No. Why not?
Play with fire. That's right.
Play with fire. Absolutely. One of my 3 boys, absolutely the most experiential learner ever. He was very young. He was 2 or 3. We had an old-fashioned dishwasher with one of the heating coils in the bottom to dry everything off. And he would always come in and to the kitchen. We would open the door to the dishwasher and he would see this thing glowing. Ooh, shiny. And he would want to reach out. We were like, no, don't do that. No, don't do that. One day he managed to reach in and grab it. And only once, you only have to kiss a hot stove once. There was much crying and soothing burn ointment on the hand. But anyway, so we're going to learn experientially today. So we have a piece of paper and I'm hoping everybody is going to draw along with me. I suppose we could call this episode Draw with Doc, couldn't we? Anyway, I am not an artist. There is no artistic talent. And I'm going to draw something here. I'm going to draw the United States relatively badly. You can draw your own country. I know we have people from around the world. If you don't want to draw your own country, draw a rectangle. You can draw New Mexico or Colorado, which are American states, which are notoriously square. So we're going to go ahead and we're going to draw the United States.
I just took a drink of coffee and almost sprayed it all over my computer screen.
I'm sorry. There's the United States. Is this awesome or what? Why isn't this guy? Why did I go into astronomy and not art, Scott? I suppose.
Yeah, you should have been a map maker.
Yeah. Oh, yeah. Mercator on a drunk.
I don't want to make you nervous, so Daniel, but we have Bonnie Spieg, and she is a history researcher from the Cincinnati Observatory Center. So
outstanding.
So
oh my gosh, I'm delighted to have you here.
Cool.
So I'm going to draw 3 cities which are basically on an east-west line with each other. And over here, I'm going to draw Washington, D.C. And this, the big F, is Fayetteville, near where you and I live, Scott. And over here on the coast, Los Angeles. And interestingly enough, these are all close enough to the 36 parallel of latitude that we can draw them essentially straight across. And since this is a map and it's an authentic type science-like program, we'll go ahead and label this direction as north. This, of course, is the east. And we've got south. No, sorry, this is west. I'm drawing sideways again, friends. There we go. North, south, east, west. I trust you're not trying to draw sideways on your paper or tablet, friends and neighbors. So we've got this. And so you're kind of by this point, my students are going, yeah, okay, this is dumb. What's the point? So think about this if we were up somewhere stationary, high above the Earth in a geosynchronous satellite. So we're in this godlike perspective. We're 24,000 miles, or what is it? 35,000 kilometers, 40,000 kilometers up. We're geostationary, and so we're looking down over the North American continent, and we're watching sunset. So here's the question. 3 cities, Washington, D.C., Fayetteville, Los Angeles. Which one gets sunset first? Or if you prefer sunrise, it works in the same order. And I'll ask you, Scott, I'll ask people to type in an answer to the chat and I'll wait. So which city gets sunrise or sunset first?
Oh, be DC, right? Sorry.
Now, did that come from one of our viewers or was that you?
That was me.
No, I want audience participation. You are correct. You are correct. And if we think of this in terms of time zones, Fayetteville is in Central Standard Time. Washington, D.C. is in Eastern Standard Time. And this is Pacific Standard Time. And there's Mountain Standard Time. We could put some city, we could put what? Albuquerque. We could put Albuquerque in here. So we have a line of 4 cities that are just about straight across the United States. So we look at these time zones and we realize, yes, okay, right now, Central Time here, it's about 4:15. Eastern Time, it's about 5:15. London is about 6 hours ahead of us. So they're about 10:15 in the evening, and so on and so forth. Los Angeles is 2 hours early. Hawaii is about 7 hours early from us. And so we look at this and we realize, oh, if we were up in this geostationary satellite, what would it look like? Well, if we were watching darkness fall, we would see the Terminator moving from east to west across the United States. And the next morning, of course, we would see sunrise appearing. And once again, the Terminator would still move in a direction from east to west. We don't usually think of it this way, Scott. We don't usually think of it this way. We could draw the Terminator.
Yeah.
And if we're talking about the sunrise, then on this side, everything is in shadow.
Yes.
And the Terminator is moving from east to west. So that's an important thing. We should write it down. I'm going to do it this way. I'm going to say the Terminator moves east to west.
Yes.
There we go. And what's interesting, the Terminator, just for everybody, Terminator is the line that separates daylight from darkness. If we look at any planet, we know the sun, acting like a single candle, lights half of the planet or moon at one time. One half is in daylight, the other half is in darkness. It must be this way, geometry, spheres, point source of light and all that. But what we don't think about is a prograde planet. We have the Terminator, and it sweeps from east to west, both for sunrise and sunset. Common misconception. Oh, the Terminator moves one way for sunrise and the other way for sunset. Like it's a window shade you're pulling up and down. I get this answer a lot.
Really?
Oh, yes. Oh, isn't it like a window shade? You pull it down, it's sunset, and you pull it up and it's sunrise? No.
Oh my gosh.
No, it's not true. And of course, if we think about this in terms of what's happening, we realize that, in fact, what we have, and I have a nice single light source here, and here we go. I've got a single light source. I have a sphere, and we can see that we are illuminating half of it. And normally we would rotate the sphere, but here it's a cue ball. It doesn't really look like much. But if we had a sphere which has some features on it, here's one now. So if I have this and I look at this and I see maybe it works better this way, and we see features coming into the daylight and then being rotated around into the darkness. And in fact, I tell my students, okay, what we're really seeing here on this diagram is evidence. And I tell them, okay, now it's time to picture yourself. Picture yourself as if you are that person on top on the Earth's surface. And as the Earth rotates around, you are carried around. Now you're in daylight, you're rotated around again, and you're in darkness. And what's actually happening is the light source does not change. The planet rotates and carries you around, first into daylight, and then about 12 hours later into darkness again. We're right about at the solstice. So this is, the equinox. So this is a very appropriate time, because equinoctius, equal night, around this time of year, we have almost exactly 12 hours of daylight, 12 hours of darkness. And so we've got this lovely situation where we now realize, the Terminator is moving from east to west all the time. And at this point, and I have students play with balls of clay and little Lego people, and I say, okay, rotate it around. And they say, oh my gosh, that means at sunrise, I'm being rotated around into the sunlight. And it's not the sun rising, it's me spinning. And they're all like slapping their foreheads and going, oh my gosh, this is amazing. And so at this point, Scott, I break out my Beatles Magical Mystery Tour album and I play them The Fool on the Hill. And you know the lyrics. I will not, don't blog off, people. I'm not going to sing. But the lyrics say, the fool on the hill sees the sun going down, and the eyes in his head sees the world spinning round. The man of 1,000 voices talking perfectly loud. Nobody seems to hear him. They think that he's just a fool. They don't seem to like him. But the fool on the hill sees the sun going, and I'm still convinced to this day, they were writing about Galileo. They were writing about Galileo, the man on the hill who sees the sun going down and the eyes in his head sees the world spinning round. And of course, he went to jail for that. The earth does not, and they made him recant. The earth neither revolves around the sun, nor does it spin on its axis, and I recant the awful heretical teachings of Copernicus. And he rose from his knees and said, "It por si muove," and yet it moves. And so we've got this wonderful thing. And at this point, people now have an image in their head, I'm hoping, that many of them have not had before, of themselves as the fool on the hill, as the song says, watching the sun going down, seeing the eyes in their head, seeing the world spinning round. Thank you, John Lennon. So they see this and they realize, oh, okay. So I'm being carried around from daylight to darkness, daylight to darkness. Okay. So now we're going to switch it up a bit. Let's go ahead and I'm going to draw some circles. And I think I'm going to just try and draw these freehand. And so we have a set of circles. And I'm just going to do my best here. This is the point where I have students who start reaching into their backpacks. They're looking for something that's round, like a coin. And I'm like, no. It doesn't matter. Your drawing is perfectly fine, even if it's not perfectly round. I think I can get 7 of these here. The last one's going to be a little small. Won't matter. So if I start out and I say over in this direction is new moon, is over there. And I think about, as I look at this, as I look at the first few days after the new moon, and what am I seeing? I've got this lovely crescent, and everything over here is dark. And no, we don't have to shade this perfectly. It's good enough. We see this brilliantly white crescent. And of course, if you're watching, it's tipped over to the horizon. But we're going to straighten it up. And if we look at the moon, we realize, oh, north, south, over here on this side is the east, and over here on this side is the west. And we look and we go, well, from new moon, the Terminator, by George, moved from the east to the west. Well, we go ahead a few days later after crescent, and what have we got? We've got the first quarter moon. And once again, we see that the Terminator continues to move from the east to the west. I'm going to get a lovely gibbous moon now. And I'm reminding my students, gee, you need to go ahead and make sure your shadow, your Terminator, starts at the North Pole and ends at the South Pole. And about this time, they say, but it doesn't quite look like that. I'm like, no, it's exactly like that. But. And at that point, I tell them, okay, it's time to look at the cue ball again. Here we've got this lovely cue ball, and we're seeing it in a gibbous phase. And we see the Terminator. And we realize if I'm shining a flashlight at a spherical object, half of the ball must be illuminated. And some of my students are still not convinced. How can it only be half illuminated? Doesn't the light bend around and come partly on the other side? And at that point, I tell them, all right, we can do this as a thought experiment, or you can try it at home. I want you to go home, and I want you to find a tennis ball and a birthday candle. And I want you to lock yourself in a very dark closet with the tennis ball and the birthday candle, and light the candle, hold it any way you wish relative to the tennis ball, and see if you can get it to light up more than half of the tennis ball. And when you come out of the closet and your friends are asking you, what are you doing in there with a candle and a tennis ball? You can tell them, I'm getting half lit. So there you are. So we finally reach the stage here where, of course, we have the lovely full moon. And we realize now the Terminator has come all the way across the disk. And the question is, well, but will the Terminator continue to move from the east to the west? And in fact, it does, because a few days later, we realize what we've got here. And the Terminator continues to move. And I'm going to bring this into center so people can see it. And we realize all that's happening is we're getting the Terminator is moving from east to west. So once again, and I'll write it out here, the Terminator always moves east to west. And so we have this situation where we realize, oh, the Terminator always goes east to west. And we can look at it and we can see it here. And we realize what we're getting is one half of the illuminated edge sweeps over, and then we wrap around, and the illumination is wrapping back around the far side away from us. And the Terminator always moves from east to west. Now, the side which is in darkness, when we start out here, we realize the western portions are in darkness, and the eastern, the daylight gradually spreads eastward. And we go back here and we look and we go, oh, the Terminator is moving across, and the eastern city gets the daylight first, and then the central, the mountain, and the western city as the Terminator moves from east to west. And so we go back here and we realize what we're actually seeing, Scott. We are actually seeing sunrise and sunset on the moon. So what the LRO people said, and we realize we are seeing sunrise and sunset on Luna, on the moon. So when we look at the phases, Scott, we're seeing sunrise and sunset on the moon. And if we take this same principle that we see here, we now realize, we can wrap this into a circle. So what I'd like people to do is I'd like people to go ahead and make a diagram. And this time we're going to put our 8 circles in a circle. And I'm going to try to keep them reasonably sized. I'm doing a better job now. Well, sort of. So I've got my 8 circles. And we often see moon phase diagrams like this where we've got 8. And I'll go ahead and give everybody a hint. Go ahead and put full up at the top, new down at the bottom. And while we chat, Scott, I'd like everybody to take a shot at filling this in. And I'm absolutely convinced that our entire audience can do a better job with this diagram than I do. So.
Okay.
So at this point, what I like to do while my students are drawing this, I like to chat with them and I say, okay, so what creates our day-night cycle on the Earth? And it doesn't take people, and I start humming Fool on the Hill again. And people start saying, well, wait, isn't it the rotation of the Earth on its axis that makes the Earth have a day-night cycle? And yes, indeed it is. And someone said, yes, you told us how, we're being actually carried around on the Earth's spherical surface. We're being carried around first into daylight and then about 12 hours later into darkness again. And the Earth keeps rotating us around through the night, across the night side, and we pop out again into daylight. And at this point, my students are really starting to get the idea that, we live on the surface of a spinning sphere. It has its axis that runs through the poles, and the Earth spins around this axis, and wherever we are, we're carried around into a daylight and darkness event that we call day and night, the diurnal cycle. And so if we've drawn this properly, And we start from new, and we realize, oh, yes, the Terminator has to always go from, and we can draw on here again. We can draw east, west. This is north. This is south. And the Terminator is always going to go eastward. And so we realize, here's what's happening. The Terminator is going eastward until the entire near side is in sunlight. So we are at full phase. And then the Terminator once again begins going. And we're still moving eastward. This time, the dark side is to the west, not to the east. And we realize, oh, we get down here. And we should end up with something like this. And we realize that we can split this up. On this side.
Now, this is as we see it in the sky. But let's say that you were somehow above the Earth.
I did this one wrong. I've got this one. I've got the circle correct, but I put the shadow on the wrong side. Because it should be coming around mostly in darkness at this point, because it's going to the new. Sorry, guys. Doc made a mistake. Dyslexia strikes again. That's what I'm going to blame it on. So we realize it's interesting. We realize we have this where we are getting more lighted. So this side is, of course, waxing. And this side is waning. And we realize, the only thing we had to do to separate this out is keep moving the Terminator constantly to the east. And so we keep moving the Terminator constantly to the east. And we take a look and we realize, when I look at any two things that are opposite from one another, I get a mirror image. Doesn't matter which way I draw it. If I look at something that's opposite, right? This way, this way, this way, this way, I get images that are reversed. And we realize, why is that? Because this side, this waxing side, is sunrise, and this waning side is sunset. And so when we move the Terminator across, it depends. Are we moving into sunlight or are we moving into darkness? Now, the interesting thing, if we were able to watch this process on the Earth, if we were in a geostationary satellite, Scott.
Yes.
So we come back and we look at our original drawing. We're in a geostationary satellite. And what we see is, here's the Terminator moving across the continent, and it's casting everything into darkness. And then we come the other way, and the Terminator crosses again from east to west, and we put everything into daylight. And we realize, if we're seeing one day-night cycle, we're seeing one rotation. And we know that's true because we're somewhere up geostationary, and we're always looking down at Fayetteville. We're directly above Fayetteville in a geostationary satellite. So we're always above here. So when we see one day-night cycle pass across, we know the Earth is rotated once. Oh, okay. Well, aren't we always seeing the same face of the moon? We are.
Yes.
We're always seeing the same face of the moon. So if we see one entire day-night cycle, doesn't it make sense then to think, I've just seen one rotation?
Lubo in
I've
China
seen-
says flat earthers will still not get it. They think that the
No, indeed.
cleverest people, they're the cleverest people in the world and will not accept anything that debunks the flat earth.
I have occasionally had someone come up to me and say, gee, I've heard about this flat earth stuff. Can you convince me? Can you show me something? And if they're an open-minded person, I will spend 5 or 10 minutes and I will talk to them. But if they're really convinced, they're pretty well armored against any facts or realistic arguments. And my dad always said I would argue with my brothers. And my dad would come up and he would put his hand on my shoulder and said, have you convinced your brother yet? I'm like, no. And he said, why not? Because he's an idiot. And dad would smile and say, you know what you know, son, when you see someone arguing with an idiot? He said, there's 2 of them.
A wise man. Yes.
He was a wise man. And so we see this one rotation and we realize we have seen one day. And so it doesn't take us very long to figure out, like the LRO people told us in the beginning, the moon takes about, if it's sidereal day, the moon's sidereal day is about 29.5 Earth days. So what we're seeing here is one lunation and for our friends out there, one lunation is one cycle of lunar phases. That's going to equal one day on the moon. And so we can watch this and we can actually take time and we can see a lunar day pass. We can see a lunar day pass. And we've talked in this program before, Scott, about watching the moon travel eastward across the sky.
Yes.
Over the days. In other words, as it goes through this cycle, we're actually seeing the moon move eastward. And it doesn't move from east to west. The moon revolves around the Earth from west to east. The Earth itself spins from west to east. We orbit around the sun from west to east. And it's called prograde rotation. It's just the fact that we happen to be on this particular carousel. We get the apparent motion, which shows us, and again, back to the Beatles song, you see the sun going down, the eyes in your head see the world spinning around. You realize if I'm seeing the sun and it appears to be moving from east to west, that's an apparent motion. It must be because I'm moving from west to east as the Earth carries me along and I spin around the Earth's axis. So I'm actually on the Earth's surface moving from the west to the east, and I move from the west to the east, which is why the Terminator appears to move from east to west. Because I'm being carried around from the darkness into daylight across the illuminated hemisphere of the Earth, and then I rotate back around into darkness again. And we realize what we're seeing here is evidence of a lunar day. We're seeing a lunar day. And indeed, when we see this, we realize, yes, one side faces us all the time. Why? Because when we look at this and we say, why does one side face us? This is my special ball here that I made to simulate the moon. And you can tell it's not properly weighted because it always lands with the same side down. It always lands with the red dot up. And of course, why is that so? Because I cheat. I cut a hole in the bottom of this ball and I inserted about 70 grams of lead, big lead sinker, a fishing weight, and I covered it back up with hot glue. And so now the ball is misweighted. And so it's always going to come to rest with the heavy side down. Indeed, the moon is the same way. The moon formed in orbit. The Earth's gravitational pull pulled the core off center by about 60 kilometers. because the Roche effect, right? The near side bulges, so everything's been pulled off center, and so the heavy side always sits down. And so when we look at the moon's perspective, where is down? Well, the moon's in our gravity well, the Earth's gravity well. So heavy side down, where does it point to? Always towards the center of the Earth. And so as the moon orbits the Earth, we see that the heavy side always points down. It's a gravitational effect because it's evidence that the moon was formed here. If the moon was not formed here, if it was formed in deep space, it would indeed, you would expect it to be perfectly concentric. The core would be centered, the moon would be very spherical, and if it became captured in our orbit, the core would very likely be very difficult after its formation to pull the core off center. After the crust was completely rigid, it would be very difficult to create a huge bulge in that side of the moon's that faces the Earth. And you might get a tide, right? The moon creates an Earth tide. The Earth rises up 3 to 5 centimeters under our feet each day, even in landlocked Arkansas, where we're in the center of the continent for all intents and purposes.
Right.
The ground rises beneath us when the moon passes overhead. We have land tides. And we know this. We know this because it has an effect on the moon. And so when we're looking at these lunar phases and we're realizing, I do indeed see a lunar day. I see the Terminator always moving from the east to the west, which allows us to put together a perfectly reasonable diagram of the moon's phases the first time. If you ask someone, Scott, if you say, here's 8 circles, sketch me the order of the lunar phases, and I'll give you 2, I'll give you new on the bottom and full on the top. Most people are not able to do this. They're not even able to get close. And even if I say, okay, here we'll make it easier for you. We'll give you little cutout pieces of paper for crescent, for gibbous, quarters, all the other. We'll give you all the shapes. I want you to go ahead and arrange them so that they're all in the correct order. People cannot do it. Now, once you go through this idea and you realize, the Terminator always goes from east to west. And then you say, I could sketch out on the moon's surface the Terminator moving from east to west. And from there, I actually can easily sketch out a correct diagram of lunar phases. Not because I've taught you the order to memorize, or I've said, let's all memorize the vocabulary words. Let's all memorize full moon, waning crescent, last quarter, waning, I could go through and say, let's all memorize these crazy things. But you know what? What we find is, in fact, that it doesn't work. We can't do it by memorization. But if we just sit down and we think based on first principles, now we own the moon. We own it. We own the cycle of the lunar phases. We possess them. We possess them not through memorization, but through understanding and comprehension. And I show this to teachers all the time. And if they're very young teachers, if they're new and just coming into the profession, they're like, this is great. This is so much better than the way I learned it in school. But if I'm talking to teachers who've been teaching for a while, we don't like this very much. We don't like this, Doc. Oh my gosh. Because, how can I convince anyone? And I'm moving my camera again, friends. Sorry. They say, oh gosh, how can I convince my principal or my headmaster that I'm actually covering the standards? How can I convince anyone that I'm actually going ahead and covering this academic material that I'm supposed to cover? And I need to, my principal expects me to come in and see me chanting, new, crescent, order, gibbous, full. They want me chanting these things and let's see some memorization. And course, that works great, especially for students who don't speak the native language well, right? We have refugees around the world. We have immigrants around the world moving from this country to that country. And of course, yay, explaining your words in your language with more words in your language always works for the new immigrant. No, it doesn't. But we can go ahead and we can take a map and we can draw across it and say, sunrise, sunset, these are concepts that make sense. The idea that, the more eastern a city is, the earlier it gets sunrise, and then the earlier it gets sunset. And so we realize where time zones come from. We've divided the earth up. And how do we do that? Well, if we have a 24-hour day and we divide it into 24, 1 hour gives us 15-degree wide segment. And so each time zone is 15-degree wide. And there's geographical, political boundaries in there, but for the most part, time zones are 15 degrees wide. Why? Because of the rate at which the Earth spins 15 degrees per hour. And if we think about these things and we tie them in together, we begin to give our students and our friends a unified concept of how the moon works. And the last thing that I mentioned to my class is I said, okay, it isn't just our moon that you own now. Because if the sun is a single candle and the earth and the moon are both half lit, half in darkness, doesn't this work the same on every planet, everywhere, with every satellite, everywhere? Don't they all rotate? The surface rotates from daylight into darkness. And as a moon orbits a planet, and on its surface, people and places are carried around into daylight and into darkness again. They said, now you own all the planets and all the moons. Everyone, everywhere, for all time, worlds without end, amen. So have we taught you about Earth's moon? Yes. But more importantly, just with a few ideas and letting you connect the dots in your head with things you already know and showing you where the connections are. We've given you ownership of all planets and all moons everywhere for all time. Because every star is a single candle. Every planet spins on its axis, some slow, some fast, doesn't matter. On Jupiter, the day would be 10 hours long. On Venus, it's like 230 some days. It's ridiculously long. Planets may spin fast or spin slow, but it doesn't matter. You might have a planet that is tidally locked to its sun the way the moon is locked to the Earth. Okay, you still have that lovely cycle of daylight and darkness that you would see watching it on from space. So yes, it always works this way everywhere for all time. And this is part of what we mean by teaching first principles, teaching based on ideas, not on facts, teaching about connections, not lists of vocabulary or facts to memorize, but teaching how things work and why they work that way. It's lovely at this point to say to the students, okay, take a baseball and a flashlight and move the flashlight around. Show me the pattern of daylight and darkness. And they're like, I see it now. Okay, go ahead and take a baseball and paint the surface and paint countries and things on it. Somebody takes a flashlight and we rotate it. And we get back to that idea we talked about very early on, our very first episode here, Scott. We're at 25 episodes, so why not hark back? Our very first episode, what shape is the moon? We said, you can look at the craters on the moon. And as you look at them, here's a circular object now. And if we rotate around towards the limb and we realize, as the crater rotates around from one surface to the other towards the limb, it becomes more elliptical. And in the center, it's always circular. And we can do that. We can study the moon and find that data. And so I posed the question to my students, okay, if you were on the moon and watching the Earth spin, could you tell that it's spherical? And someone said, well, yes, because you would see the eastern cities emerge into daylight first, and then the continent would come around. Continents, areas like Australia, Africa, Americas, they would become foreshortened as they moved around to the limb. I go, oh, that's right. And so we'll end up, Scott, we'll end up with this one last idea, and we'll hearken back to my young friend who said, can you give me one thing to show me for the flat earth people? And so I'm going to go back to my drawing board here. I've taken my other Zoom camera into work. That's why I'm having to play this game today with move the camera. Sorry, everybody. So here we go. And if this is indeed, if the earth is indeed flat, let's take a look. The earth is indeed flat. And so if the earth is indeed flat and it has a certain thickness, well, the center of mass is still the center of gravity. So you ask yourself, which way is down? Well, if you were here in the center, down would always point towards here. But if we were a little bit away, we would realize, oh, down points progressively at greater and greater angles. So in fact, if we were standing on a flat earth, it wouldn't feel flat, because as we walked this way, it would feel like we were trudging up a hill. We would in fact feel like the earth was a half pipe, right? We would feel like we were on the inside of a cylinder and walking up toward the edge. And of course, so if the earth felt like it was curving up this way as we got closer to the edge, as we moved away from the center, we would feel like we were going uphill in any direction. Do we feel that? No. Is there evidence that the different places on the earth have a different direction of gravity that is not parallel to the surface or perpendicular to the surface? Of course they don't, because in the spherical model, down is always toward the center, and that's why gravity is always perpendicular to a level surface. And so just simple observations like this prove to us that the earth must be a sphere, that in fact, we can observe a full day-night cycle on the moon. We can see the Terminator move across that world, and we can experience it as we are dragged around across the Terminator on ours. It's a matter of shifting your perspective from off this rock out into space to see the world in the same glorious perspective that our astronauts get to see it.
Mm-hmm.
And that the Apollo astronauts got to see it more than anybody. Nobody's gone beyond low Earth orbit since. So you see these lovely pictures from the ISS where the gently curving surface of Earth, and we all know that wonderful picture from Apollo 8 of the Earth rising above the horizon of the moon on Christmas Day in 1968. We all remember that. If you were here, you do. So we need to teach concepts. We need to teach ideas. We need to teach people to think. And we need to teach people to lift their perspective from off the very small plot of ground on which we all stand and walk about. And when we do that, we give more than just a set of facts. We give a perspective and an understanding that's priceless.
That's right. And they've conceptually figured it out, you know, and Harold Locke makes this point. He says, if I don't conceptually create a full idea in my head, then I don't remember it, you know.
Very good. Precisely.
And, he says, therefore, I'm a slow learner. I would say that maybe the people who are spending more time trying to create conceptual thoughts in their head, or, you know, they take more time than someone that's just simply memorizing things, you know?
You know, I'm going to object with Mr. Locke to the idea of slow as a pejorative, as something that's discouraging. Benjamin Bloom said that we consider giftedness in the United States all wrong. We consider people that learn fast to be gifted, and people who are slow, that's a label that we put on them that's not so good. He said, you know, the speed at which you learn doesn't matter. The fact of whether or not you get there does. Bloom said, would you rather have someone who learned a little bit fast or who was a slower learner but got it all completely? Consider you're lying on a table waiting for someone to take your appendix out. What kind of learner do you want holding the knife? I want that fellow who has gotten everything down, thank you very much, and I don't care if they did it in 7 years or 9 or 12.
Right.
I want the person who has mastered the subject matter. I want the person with the complete understanding. So I'm going to object to our viewer's description of himself as a slow learner. Let's just say that he is a very thorough learner, and when you get there, you get there.
And learning takes time.
It does. I've been here a long time. This is my 42nd year teaching astronomy, Scott. I'm still learning about it, still learning new stuff.
Sure.
And so I'm hoping everybody learned something today. I'm hoping everybody enjoyed the program. And next week, we're moving towards Halloween, which is an American holiday. It's actually a very old European holiday, celebrating the dead and our ancestors. Well, we're going to talk about dead things next week, Scott. We're going to talk about dead galaxies, and it's going to be an exciting program. And we're going to talk about where do galaxies go when they die, and if it's a murder mystery, of course, who killed them and how. Was it Professor Plum in the library with a candlestick? We shall find out next week when we talk about dead galaxies. And how do you kill one? How do you kill one? We went back to that idea when we talked about the origin of life, and we're talking about life on Mars. And we said, oh, gee, if you ever had life on Mars, what could you do to sterilize an entire planet? And you need a lot of Lysol. You need a lot of bleach.
Maybe more than that.
Yeah, you need more than that. We said you need a solar cataclysm to sterilize a planet. Well, how do you kill a galaxy, Scott? If it's hard to kill a planet, how do you kill a galaxy?
What does
We're going
that mean
to
anyway?
learn how. What's that?
I said, what does that mean anyways, you know?
Yes, indeed. What did the nice galaxy do to you that you wanted it dead? What does it mean to have a dead galaxy?
Right.
So we're gonna have a murder mystery next week, and
Okay.
I'm going to come in as Sam Spade or Philip Marlowe or somebody like that, and we're going to do the hard-boiled detective. So we're going to have a detective show next week. Who killed the galaxy and how did it die?
Okay.
So we shall have an interesting list of suspects, and we'll see where we go.
Okay. All right. Well, that's great. Now, for those of you who were looking to get the study guide for this, we'll be putting it up. It'll either be up this afternoon or tomorrow, so you can
Tomorrow,
go
I
to
think. Yeah.
the How Do You Know page and download it. It's the 25th episode. And so, and then on Tuesday, we will have the 63rd Global Star Party. This is an interesting one. We have Deepti Gautam, who's been on our program many times. She's a young amateur astronomer finishing up high school, and she is with the Nepal Astronomical Society. And so she's got a lineup of amateur astronomers and space enthusiasts from Nepal. They'll be giving presentations.
Sounds exciting.
Yeah, they'll be great. And then on the weekend, on Saturday, we'll have the 64th Global Star Party. And this is called the 45-degree Star Party because it will be held by the Royal Astronomical Society of Canada at 45 degrees plus, and the Royal Astronomical Society of New Zealand, okay, 45 degrees south. And so it will start at our regular time, which will be at 7 p.m. Central, which is 8 Eastern, and 1 p.m. New Zealand time the next day. Okay, so because that's just the way it works.
There's time zones and
Time zones,
exactly.
exactly.
Yeah.
Right. And so we hope you watch and are entertained and learn more. So thank you very much for watching Dr. Barth today, and for applying your mind towards figuring out the phases of the moon just in your head. So anything else for you today, Daniel?
No, I'm good, and I'll
Okay.
get that study guide up for everybody. And it was on purpose. I didn't want anybody to come in with a preconceived notion today.
That's right.
So
Okay.
thank you all for playing along.
All right. Okay. Well, we'll see you. And as my good friend, my good friend, oh my goodness, I've forgotten the name again.
Dear.
But just keep looking up. He's from
Horkheimer.
heaven, pointing down, laughing.
Jack
Okay?
Horkheimer.
Jack
Right,
Horkheimer.
Jack
That's right.
Horkheimer?
Oh my God.
There we
I'll
go.
tell you guys a funny story about Jack Horkheimer and about Clyde Tombaugh. Okay, back many years ago now, Clyde Tombaugh was visiting the Riverside Telescope Makers Conference, and this is a star party that I attended. Oh, I don't know, maybe 20 years in a row.
Right.
Anyways, I had my Sky Atlas 2000, and I'll bring it sometime and show you guys, but there's many interesting signatures, and one of them is by Clyde Tombaugh, okay? Now, I had Buzz Aldrin sign my star chart, of course, David Levy signed it, and a bunch of other people, a bunch of famous people and not so famous people have signed that star chart. But I go up to Clyde Tombaugh and I say, Clyde, or Mr. Tombaugh, I didn't call him Clyde. Mr. Tombaugh, would you please sign my star map? And he looked at me with kind of a scowl on his face and he says, $5. And I thought he was joking. And so I'm laughing. I'm like, oh, okay, yeah, right, $5. And I'm handing it to him and he goes, no, $5. And so I said, I dig in my wallet, I give him the $5. I said, okay, put down Clyde Tombaugh, I discovered Pluto in 1930. Which he did, okay? And I think that's really cool that it's in there. So I go to the Winter Star Party, and some of my friends had already tipped off Jack Horkheimer. I didn't know he was going to be there, okay? But he was there at the Winter Star Party in Florida. And I go to ask him to sign my star chart. And of course, he tells me quite sternly it's going to be $5 to sign it. And I'm going, darn, not another. So anyhow.
I will tell you my Clyde Tombaugh signature story.
Okay.
I went to see Mr. Tombaugh when I was in my early 20s, and he was appearing at a star party and showing everybody Pluto. It might have been 1980, right? That would have been the 50th anniversary, something like that. Anyway, sure. So I went up and he gave a presentation. We went out and we were going out to look at telescopes, and he was sitting there. And I came up and I said, Mr. Tombaugh, I have a book by a mutual friend of ours, and I was hoping you would sign for me. And he looked up at me and said, kid, who the hell would you know that I know? And I said, I brought Newton's Principia. And he sort of stopped for a minute. He smiled and goes, yeah, okay. Ike's a friend of mine. I'll sign for you. And so he signed my copy of the Principia.
Yeah, very good.
I like Ike. So
very cool. Well, anyways, the reason why you guys want to attend star parties when we can start doing them again is a lot of times some very, very cool people show up, okay? Because, the discoverers, the astronauts, these luminaries of space and astronomy often show up at amateur events, and they love astronomy the way that we do, and so it's a good chance to mingle with these people. A lot of them already get it, that if you're interested in participating in the amateur astronomy community, that you're really kind of one of them, and you're part of this fraternity of astronomy, science that spans back many, many years, centuries, maybe
Millennia.
thousands of years, millennia. Exactly.
Right.
Exactly. And it's still going on. We're still discovering things. We're still creating new hypotheses, new theories. We're on this giant adventure trying to figure out where we are in the universe. So we hope you join us on more of these virtual events, but coming up
Someday
next
soon.
year, we have real events planned. And so
Yes.
hopefully we're out of most of this COVID lockdown scenario, and we'll continue to do virtual things as well, because we think it's a great way to continue to spread the word. And so I hope you agree, and we will see you tomorrow on Global Star Party. So take care.
Thanks, Scott. Bye-bye, everyone.
Bye.